This project focuses on improving the design of the roof handle, a widely used component in cars for passengers' comfort. The aim was to create a lighter and more functional design by optimizing the existing handle's dimensions. The team utilized Bezier surface to construct a model based on the optimized handle grip results. The final model was then converted into a STL format and prepared for 3D printing. In summary, the project involved optimizing the roof handle, constructing a model using Bezier surfaces, and preparing the final design for 3D printing. Our motivation is to achieve a more reliable and innovative design.
Cars have become a necessity rather than a luxury in today's society, and as a result, every component of the car has become essential. Despite being a seemingly insignificant part, the roof handle is crucial to ensuring passengers' comfort and safety, preventing them from being thrown around during acceleration. As such, the roof handle remains an important part of the car. In this project, the aim is to improve the comfort and aesthetics of the roof handle while reducing production costs by minimizing weight. The goal is to create smoother surfaces for the handle, resulting in a more comfortable and visually pleasing design. The red numbers on the sides and the endpoints of the empty inner squares indicate the nodes that will be used in the optimization process. These nodes are stored in matrices within the code, and these matrices are further stored in a matrix array called node NRS, which makes it easier to access the nodes in the graph using the code. This process is known as meshing, which involves converting the design model into a mathematical model by dividing it into mesh elements. In this study, the size parameter used were 240 mm in the form of a rectangle, and a mesh size of 4 mm was chosen to optimize the time required for the process. Topology optimization involves more parameters than just the design dimensions. Table 1 in MATLAB shows a section of the code with the selected values for these parameters. Raw, trial, and error, various adjustments were made to these parameters to achieve the desired design. Boundary conditions are also critical parameters for topology optimization. These conditions include specifying where forces will be applied, where the design will remain empty, and where it will be fixed. In this study, the design was fixed at 40 mm size in the X and Y directions from the right and left bottom. A 10 Newton force was applied at a 60 mm level in the Z direction and between 40 mm and 160 mm in the X direction. The optimization process was also conducted using Fusion 360 software. Initially, a volume with dimensions of 200 mm, 80 mm, 40 mm was designed, and fixed points were determined while applying force. This diagram is illustrated in the figure 3. The optimization was performed using 3D optimization with 1 Newton force applied, 0.2 volume fraction, and 3 mm mesh size. In addition, the bottom corners were fixed during the optimization process. First, three-dimensional topology optimization was made in MATLAB according to the fixed parameters. Topology optimization. Afterwards, modeling was done with Bezier surfaces, taking the resulting image as a reference.
Each Bezier surface is self-contained and does not rely on any other surfaces. The method was achieving continuity between two surfaces is determinate, and by doing so, the surfaces become interdependent. Bezier surfaces can be connected with different types of continuity. G0 continuity connects the final control points of one surface to the initial control points of the other, ensuring there is no space between them. G1 continuity provides a smoother junction by also aligning the tangent vectors at the connection point. C1 continuity is dissimilar to G1, but also ensures that the distance between the first two control points of the second surface is equal to the distance between the last two control points of the first surface. MATLAB and topology optimization code were used to explore design possibilities and identify the optimal topology for the desired shape. This process provided a foundation for developing the final design, which aligned with the project's requirements and intentions. Fusion 360 was used for topology optimization, allowing the team to develop an optimal design that met project requirements. The resulting shape served as a starting point for further refinement, considering various factors including functionality, ergonomics, aesthetics, and manufacturability. The use of Fusion 360 and topology optimization proved to be an effective approach to designing the desired shape. Here we created our model using the Bezier surfaces. The model was created taking into account the continuities. The Bezier surface model in isometric view in figure 12 and the figure 13 is Bezier surface model in ZI view. Figure 14 is Bezier surface model in XI view and figure 15 is Bezier surface model in XZ.
The design of a car roof grab handle was identified as a priority in the project. The team established the necessary parameters that were required to design the handle. After determining the topology, the next step was to optimize the topology to arrive at the desired design. The team leveraged the results of the optimization process to generate ideas for the design, which included the modeling a Bezier surface. During the surface modeling stage, the team ensured that continuities were taken into consideration. This was important because the continuity of the surface plays a significant role in the final design of the car roof grab handle. The team paid close attention to the smoothness and flow of the surface to ensure a more ergonomic and aesthetically pleasing design. By optimizing the topology and carefully modeling the Bezier surface with continuity in mind, the team was able to achieve a design that was more ergonomic and aesthetically pleasing than the original intention. The final design of the car roof grab handle not only meets the functional requirements but also enhances the overall look and feel of the car's interior. The team's attention to detail during the design process led to a successful outcome, resulting in a product that meets both form and function requirements. Firstly, the optimization we have made can be diversified and made available for different vehicle segments. For example, it could be the console handle we hold on to when getting in a pickup truck or the handle in a luxury car. Secondly, this optimization can be applied to public transportation vehicles such as subway, train, and bus, which have different objectives and can be optimized under different load and boundary conditions. Lastly, a more futuristic idea could be developed, which will be used mostly in luxury and executive cars. This system will retrieve information from a database based on the occupant's fingerprint and automatically adjust the seat settings, climate control, message settings, and other features. We would like to thank our instructor, Associate Professor Recep Muhammed Görgül Arslan, for his help and support. Thank you for listening to us.